Now coming to the preparation of hydrogen, we have already seen the similarities of hydrogen with alkali metals as well as dissimilarities. Similarly, similarities with halogens as well as dissimilarities. Already we have discussed all those things. Now we'll come to the preparation of hydrogen. It's very important to understand it. Now, in the preparation of hydrogen, what you find is that you will find the elements which are placed higher in the metal activity series. Now, you need to understand the metal activity series. I told you to remember the metal activity series of poem. If you still don't remember, once again I can say you. Let me write the series. It is popular scientist can make a zoo in the low humid country more satisfactory. Still I don't have the space here, you can write gold and platinum. So in this way, this is your metal activity series. Alright, we need to remember it. Alright, and we are preparing this one, hydrogen. Our aim is to prepare hydrogen, alright, from different metals. Now, first of all, these metals are highly reactive in nature. Potassium, sodium, calcium, magnesium, aluminium, all these are highly reactive. But the most reactive is your potassium, sodium, calcium. They are the most reactive in nature. How can we say that? Now, if we put potassium or sodium, suppose into water, alright, you know what's going to happen? It is going to melt, alright, it will catch fire. An explosive reaction will be there. With potassium, when you drop potassium into water, an explosive reaction will be there. Alright, for that reason only we store potassium and sodium under inert solvent. Under inert solvent. Inert solvent is kerosene. We store it under petrol or under kerosene we store it. So that sodium, potassium should not come in contact with the air also. What will happen if it comes in contact with the air? It will react with the moisture which is present in the air. And it will undergo what you can say a vigorous reaction, that is, it's going to catch fire. Alright, to prevent this, what we do, we keep sodium, potassium under kerosene. Under, we can say that petrol or diesel we keep it, so that it will not come in contact with air. It will not come in contact with the moisture which is present in the air. So you can understand how reactive it is. How reactive it is. So same sodium and potassium, when you are putting it into water, let us say a small piece of potassium or sodium, you will cut it, because sodium potassium is very soft. It can be cut with a knife, even if it is a metal. Even if it's a metal, alright, but it is so soft that it can cut with a knife. We can cut with a knife, alright. So we'll cut a small piece of sodium and potassium and we'll put it into water. It will give a highly exothermic reaction. Highly exothermic reaction. That is, gas will be evolved, hydrogen gas which is evolved, that only helps in catching fire, because you know hydrogen is a highly inflammable gas. If you do not know, you will be studying it in the properties of hydrogen. I will be telling you about it. So in this way it catches fire. Alright, it is so highly reactive, hydrogen is. So it burns with a lilac flame. Which one? Potassium. It burns with a lilac, bagni, it is said to be as, or crimson color we can say that. Similarly, sodium, when you are putting into water, it gives a highly exothermic reaction. Of course, cold water it should be. Both the cases cold water, mind it, not hot water. Again I am saying normal water, cold water. Alright, sodium melts into a silver globule. I said you, both the metals is going to melt first, which evolves what you can say hydrogen gas, and it also catches fire, we can say that. But here, the sodium burns with a golden yellow flame. Alright, it burns with a golden yellow flame. So what you find is that in both the cases you find that when sodium reacts with water, potassium reacts with water, K plus H2O, it will give you what? KOH plus H2. You can balance this. Similarly, Na plus H2O will give you NaOH plus H2. You can also balance this equation. Alright, you can also balance this equation. You need to balance it also. If you say, it's very easy, 2K plus 2H2O will give you 2KOH. Plus hydrogen is 4, here hydrogen is also 4, oxygen is 2, oxygen is 2, this is done. Same thing with here also we are going to do. Finished. So easy. So in this way, in both the cases, it is very difficult to collect the gas, because I said no, the reaction is highly vigorous, it is highly exothermic, it catches fire, it is highly explosive also. In case of potassium, it may burst open, the vessel may burst open, it is so explosive in nature. Alright. So hence, we can say that. Now, In this way, what we do is that we wrap it, that is sodium potassium, in a wire gauze, got it? And or it is amalgamated with that is mercury. The base metal is mercury. Amalgam means where the base metal is mercury. Got it? We take sodium and we put it into mercury and we mix it thoroughly. Got it? You know, mercury is a metal. Got it? So, or potassium we put into mercury, we mix it thoroughly and it forms small balls, and that particular balls we put it into water. So the reaction becomes less vigorous. By that way we can collect hydrogen gas from sodium and potassium. Alright, we can do it in that particular way. Clear? Or for the steady flow of the gas, what I said you can wrap the sodium and potassium metal in a wire gauze and put it into water. Put it into cold water. Then hydrogen gas will be evolved, but at a steady rate. At a steady rate by which you can be able to collect the hydrogen gas. You will be able to collect it. Alright, fine. Now with calcium the reactivity is less, because you know, as you come down the series, down this particular group, the reactivity is decreasing. For that reason I said it's a metal activity series. And the topmost, the most active metal, but definitely when you are coming down, activity is decreasing. Alright, the reactivity is decreasing. So with potassium it is less vigorous compared to sodium and potassium, so to say. With calcium it is less vigorous compared to sodium and potassium. With water we can say that. Here also hydrogen gas is readily evolved, but it is readily evolved. It also calcium reacts with water to form what you can say calcium hydroxide. You can say that Ca plus H2O will give you CaOH whole twice plus hydrogen gas is evolved. We can say that. Clear? So in this way we can say Ca plus 2H2O. So 4 hydrogen. Here also it is 4 hydrogen, 2 oxygen, 1 calcium, done, balanced. So in this way also what you can say, but it is less vigorous we can say that compared to sodium and potassium, and it does not melt, it sinks in water. Calcium sinks in water because it is quite heavier, we can say that. Clear? Now coming down to magnesium and aluminium. Got it? So magnesium and aluminium, it reacts with steam, remember it. It reacts with steam. Magnesium, aluminium, zinc, it reacts with steam to form the respective oxides and hydrogen gases evolved. But here what you find is that, what I said you, in this case it was a cold water. But magnesium, aluminium, zinc, they do not have any reaction with the cold water. By this what is being proved? That magnesium, aluminium, zinc, all these are less active metals compared to sodium, potassium and calcium. Definitely, because sodium, potassium, calcium, they react with the cold water, but they have got no reaction with cold water. They react with the hot water, we can say that. They react with hot water, and hence it reacts with hot water to form what? For example, magnesium reacts with hot water. It should be hot here. Here nothing means cold water or normal water. It is going to give you what? Magnesium oxide and hydrogen gas is evolved. Similarly, if you take zinc, you will get zinc oxide and hydrogen gas. Similarly, if you take aluminium, you will get aluminium oxide and hydrogen gas. But let me tell you here that the reaction takes place for a short period of time. After that, the reaction stops. Do you know why? Because over the surface of magnesium or zinc or aluminium, a layer of oxide comes which prevents further reaction of that particular, what you can say, with hot water to liberate the hydrogen gas. Again I repeat, let us say this is magnesium, let us say, or zinc or aluminium. Now when I put into hot water, initially you will get some hydrogen gas according to this equation. But after that, the oxide layer, it settles over the surface of this particular metal, it settles. Now will that metal now come in contact with hot water, or the oxide will come in contact with what? Hot water? Definitely oxide, because oxide settles over the surface of the metal. Which metal? Again I repeat, magnesium, aluminium, zinc. So these oxides are insoluble oxides and they do not allow to react with hot water to liberate the hydrogen gas. So initially you find that the reaction takes place, little bit of hydrogen gas is evolved, but after that the reaction generally it becomes very slow or it stops after some time. The reason I have said you. Alright, so what you find is that the rate of reaction is fastest in case of magnesium and slows down in case of aluminium and zinc and iron. Got it? It is fastest in case of, in this particular series, that is magnesium, because this reacts with cold water. I have already said you. Now this reacts with hot water, but this reacts with steam. Alright, with iron the reaction is so slow that it reacts with steam, I should say. It reacts with steam. Alright, so when iron reacts with steam, what it happens? See here. Fe plus H2O, that is H2O, that is your steam here, not hot water also. What is going to form? It is going to form magnetic oxide of iron or triferric tetraoxide of iron. This is called magnetic oxide of iron or triferric tetraoxide of iron, and hydrogen gas is evolved. Alright, so 4 oxygen means 4H2O and it will be 4 hydrogen here. 4 hydrogen here. You will be getting it. So in this way you are getting it, that is with steam the reaction takes place. I have written it here. Alright, I have written it here, the reaction takes place with steam, moreover. Alright, now in case of that is, I have said you that is in this series, that is in this particular series you can find the magnesium is fastest and all these are slower. With iron it is so slow, that is with hot water it is so slow that we react with steam further to make the reactions, we can say, further possible. Now one more thing about iron, let me tell you. That is with iron the reaction is actually reversible in actual practice. Actually it is reversible. The reaction is almost irreversible and proceeds from what you can say left to right, because hydrogen is continuously blown out in contact with iron by the current of steam, we can say that. Here, if you want to make the reactions irreversible, then what you need to do is that you have to continuously remove the hydrogen. Alright, with help of steam you remove the hydrogen from this. Otherwise, the reaction becomes reversible. This one is reversible. But if you want that it is irreversible, if you want that the reaction should go in the forward direction, what you have to do is that you have to remove hydrogen continuously. Continuously remove hydrogen. So that what you will find is that it makes the reaction, what you can say, irreversible. So that when you remove hydrogen from the site of the reaction, then the reaction is going in the forward direction. Otherwise, what happens? Fe3O4 will react with hydrogen to form Fe plus water. It is going to steam. It is going to form. What I said? The reaction is practically, in actual practice, is reversible in nature. Got it? The reaction is almost irreversible if you remove hydrogen from the site of the reaction. Got it? So, how to remove it? By the help of steam, you remove the hydrogen. You pass the current of steam, so the hydrogen gas also will be removed. We can say that. So, in this way, you find it out. The reactivity, it differs when you come down the series, we can say that. Now, next is, I was talking about metals. Okay, you understood. Now, I will come to some non-metals also. Some non-metals also we will see that non-metals like carbon, when it reacts with what you can say steam or hot water, it will give you, that is the hydrogen gas is evolved. Clear? That is C plus H2O, that is steam, we can say that. It will give you CO plus H2, hydrogen gas is evolved, we can say that. Clear? When C, that is a white hot coke, we can say that, reacts with steam. White hot coke, this is C, that carbon is. It reacts with this to form, what you can say, now this particular one I'll put in a square bracket. You know what is being formed? It is actually an equal volume of carbon monoxide and hydrogen, which is known as what? Water gas. Which is also otherwise known as water gas. An equal volume of carbon monoxide and hydrogen is being formed and is used for the industrial preparation. You will see in further preparation of hydrogen, for the industrial preparation of hydrogen, I'll be teaching you a process called as Bosch process, we can say that, where I'll be using the water gas to manufacture hydrogen. Got it? In industries, we can say that. Now, that is silicon can also be used, because you know carbon and silicon, they come to the same group, that is group 14. Got it? It can also be used. Clear? So, what I am going to get it? Same thing. I am going to get it nothing but silicon dioxide. Like here carbon monoxide, I got it. I will get silicon dioxide plus hydrogen gas is evolved. Alright, now this is not any particular gas. Like this is called as a water gas. An equal volume of carbon monoxide and hydrogen. Equal volume you can see of carbon monoxide and hydrogen is called as water gas. But we don't have any such name for it, because here SiO2 and hydrogen is collected separately. Now to balance it, of course this is also steam. Of course. To balance it, I will be putting this, so hence no square bracket will be here. Alright, understood? No square bracket here. Here I put a square bracket because together it is called as water gas. But initially I put it, now also I am putting it. But it is not required. Why? Because this is collected separately. SiO2 and H2 is collected separately. So hence I no need to put the square bracket here. Alright, so in this way, from non-metals also we can prepare hydrogen, we can say that. We can also prepare hydrogen from non-metals. Clear? So in this way, what you find is that this particular metals and the non-metals react with cold water, they react with hot water, they react with steam to give you the hydrogen gas, we can say that. Now, next is what we find is, like up to iron we have come it. Now, tin and lead, when it reacts with steam or hot water or cold water, we don't get any hydrogen gas because it is quite less active in nature. quite less active in nature. So there we have to use acids. Remember it, we have to use acids to prepare the hydrogen gas. Because you know, when metals reacts with acids, it gives salt plus hydrogen gas is evolved. I'm going to write the reaction, don't worry. I'm going to write it down. Alright, so in this way, but don't use acids in case of potassium, sodium, calcium and all those things. Because you have seen it, with potassium, sodium, it reacts vigorously with cold water only. With cold water only, the reaction is very vigorous, very vigorous. So don't use what you can say acids for the production of hydrogen from potassium, sodium and calcium, mind it. Theoretically, I can write it out, no problem. Theoretically, it is possible that potassium reacts with HCl to form KCl plus hydrogen gas is released. Alright, this is theoretically possible. Potassium reacts with sulfuric acid to form potassium sulfate and hydrogen gas is released. It is theoretically possible, but practically it is not possible because I said with the acids the reaction is very vigorous. It's very fast, we can say that, with acids. You cannot imagine that how vigorous and how exothermic the reaction will be, because you just imagine with cold water which is so vigorous. So with acids it is not at all imaginable that how it can be, how vigorous it can be, how fast the reaction will be. Got it? So theoretically this reaction I can write it down, but practically we never do it. So generally to prepare hydrogen, calcium to a certain extent I can take. We can take magnesium, aluminium, zinc, we can take it to prepare hydrogen from acids, we can say that. Like magnesium, when it reacts with H2SO4, it should be dilute. Understood? All these are dilute. Nothing is written means here means it is dilute acid, it's not concentrated. I'll tell you also, if you take concentrated, what is going to happen. So MgSO4 and hydrogen gas is evolved. If you take here concentrated acids, then chlorine gas also will be evolved. We can say that along with it. And you may not get hydrogen in adequate quantity. The yield of hydrogen will be low. Alright. So here also same thing, you may get sulfur dioxide gas. Alright. You may get sulfur dioxide gas, and you know, concentrated sulfuric acid. If you take, it is not concentrated here. I told you already. It is dilute. If you take concentrated, then you will be getting sulfur dioxide gas, and concentrated sulfuric acid also acts as a oxidizing agent. It will give you nascent oxygen, and water also will be produced in that particular case instead of getting hydrogen gas. So generally we take what you can say acids to prepare hydrogen with the less active metals. These metals we take it. Generally we take that is zinc. I can take it. Now zinc reacts with dilute sulfuric acid to form zinc sulfate and hydrogen gas is evolved. You can see zinc is basically used for the laboratory preparation of hydrogen. You will be seeing it. I'll tell you the reason also why I am using zinc in that particular case. We can say that. You can take aluminium also. Like aluminium reacts with sulfuric acid to form aluminium sulfate and hydrogen gas will be evolved in this way. So the less active metals can react with acids to give you what you can say hydrogen gas. We can say that. The less active metals, mind it. But don't take nitric acid here. Don't take nitric acid, because nitric acid will evolve hydrogen gas. Alright, very dilute nitric acid. Listen carefully. Very dilute nitric acid will evolve hydrogen gas only with two metals, magnesium and manganese. Very dilute nitric acid means what? That is 1% acid, means 99% water and 1% nitric acid if you take. 99% water means, suppose if you are taking 100 liters of nitric acid, in which 1 liter of nitric acid will be there and 99 liters of water will be there. That is called very dilute nitric acid if you take it. Then magnesium and manganese reacts with very dilute nitric acid to liberate hydrogen gas, so to say only these two metals. Why not other metals? Because other metals will what you can say will react with nitric acid to not liberate hydrogen gas. It will react with oxygen, because nitric acid is a strong oxidizing agent. It gives you nascent oxygen. This nascent oxygen reacts with hydrogen to give you water. So you will not get hydrogen. Listen carefully. You will not get hydrogen. You will get water instead of hydrogen. Only magnesium and manganese with very dilute nitric acid, just now I said you, will give you hydrogen. We can say that. Now lead cannot be used for the preparation of hydrogen with dilute acids. Why? Because if you take Pb plus HCl, alright, or Pb plus H2SO4. So Pb plus HCl or H2SO4 will give you a salt, which is known as, either here in case of HCl you will get PbCl2 and hydrogen gas is released. With Pb plus H2SO4 will give you PbSO4 plus hydrogen gas is released. But what is this? It's a downward arrow. Downward arrow means it's a precipitate. So it forms an insoluble PPT, PbCl2 and PbSO4. Listen carefully. It forms an insoluble precipitate and settles over the surface of the lead, due to which the reaction stops after some time. So lead cannot be used. Alright, so let us say this is lead. I am using HCl or H2SO4. What is going to form? Insoluble PbCl2 and PbSO4 is going to form, which is going to settle over the surface of the lead, and hence the reaction stops further. The reaction does not take place further. So lead cannot be used for that particular purpose to prepare the hydrogen gas, so to say. Lead cannot be used. With the tin, the reaction is can be considered. With the tin, the reaction can be considered, but it is less vigorous in nature. With tin, we can say that the reaction is less vigorous, very less vigorous, because tin is less reactive in nature, because you can see is that tin is just above the lead, we can say that. Alright, so we can use with tin. Got it? We can use with tin plus HCl, I can say, will give you stannous chloride and hydrogen gas is evolved, but it is very less vigorous, means the reaction is very slow. That is what I mean to say. Now metals like copper, mercury, which are below hydrogen, silver, they do not react with HCl or H2SO4 to liberate hydrogen gas. HNO3 cannot be used, I said you already, because it is an oxidizing agent, it gives you nascent oxygen. Alright, so if at all hydrogen gas is used, is evolved, it reacts with nascent oxygen to give you water. So HNO3 completely ruled out. Nowhere we are taking HNO3. Only with magnesium and manganese I have told you, with very dilute nitric acid. So here I cannot take copper, silver, mercury to prepare hydrogen gas. Why? Because they are below hydrogen in the metal activity series. For that reason I wrote this metal activity series. They are below hydrogen in the metal activity series, and they do not displace hydrogen from acids. The metals which are above hydrogen can displace hydrogen from acids, but the metals which are below hydrogen cannot displace hydrogen from acids. So if you take Cu plus HCl, no reaction. If you take Ag plus H2SO4, no reaction, because it will not displace hydrogen from acids, we can say that. There are also certain metals are there which are amphoteric in nature, like your zinc is there, aluminum is there, tin is there, lead is there, which not only reacts with acids but also reacts with bases, we can say that. I said you with lead, practically we do not do with lead, because I told you the reason, because it forms a sulfate or a chloride and insoluble salt, we can say that. But we can do with bases, like zinc reacts with the base to form Na2ZnO2 plus H2, because zinc is an amphoteric metal. Amphoteric means the substances which reacts with both acids as well as with bases. Generally metals are basic in nature, so they react with acids to liberate hydrogen gas. But there are certain metals, certain elements like zinc is there, aluminum is there, tin is there, lead is there. They not only react with acids but also they react with bases to liberate the hydrogen gas, because they are amphoteric in nature. So zinc reacts with sodium hydroxide to form sodium zincate and hydrogen. Similarly, if you take aluminum, reacts with sodium hydroxide and water to form, what you can say, sodium aluminate, and hydrogen gas will be evolved, we can say that. Clear? In this way. Clear? So this is the unique nature of zinc, aluminum, tin, lead, we can say that. Clear? Acha. So, and moreover, the aluminates which are formed, or zincate which is being formed, or stannate, suppose if you react with tin, it will form stannate. Alright, like Sn plus Na, which will give you Na2SnO2 plus hydrogen. Alright, stannate, zincate, aluminate, they are soluble in water. They are moreover soluble in water. They do not form an insoluble substance. They are soluble in water. So readily hydrogen gas is evolved, we can say that. And the metals we are taking in the powdered state to make the reaction faster, we can say that. Clear? The reaction takes place only on heating with the metal with concentrated alkalis. So these metals, these alkalis which you are taking, it should be concentrated one. Alright? Clear? It should be a concentrated alkali. Then only the reaction will be possible. So these are the reactions of different metals with acids, bases, cold water, hot water, steam, non-metals, I've said you everything. Okay? Thank you.